Welcome to polynomial behavior. And watch out, folks, these polynomials tend to be a little outrageous in their behavior. Let's get started. After this video is over, you should make certain that the following ideas are located in your notes. Zeros and their multiplicities, flexing and the number of zero multiplicity associated with that, touch and turn or bouncing and the multiplicity of zeros associated with that, inflection / turning points and the local max or minimums that they create, how to write the polynomial function given its zeros and perhaps 1 point, and the number of bends versus a polynomial degree. I think for notes purposes, if you don't have this as a hard copy in front of you, you're not able to print it out, I think that you want to just grab these pictures and make sure that you have the horizontal scale mainly. All right, and now let's get going. Press pause and copy the pictures if you're not already there. Now what we want to talk about are the zeros and their multiplicities, right? So this idea that some of these zeros are going to come at us a little bit more than once. So when we take a look at the function up here, we see that this is in factored form, right? And so we know that we have x equals -6, that's a -6 right there, and x equals +7, right? They only happen once. And I see that I have x plus 6 only one time, x minus 7 happening only one time, and I notice that the function goes through the x-axis. And so when we see this multiplicity of 1, right, the function goes through the x-axis. So that's a one and done. -6 happens once, +7 happens once. Versus over on the other function, I notice that it goes through here, so there's only one, but then it turns and touches right there, and that's at +7. Notice we have a factor of x minus 7 squared, and at 7, this does a turn and touch, or touch and turn rather, has a multiplicity of 2. And so that lingo, touches and turns, is how we're going to remember that piece right there. And just a reminder that the real zeros of a polynomial correspond to the x-intercepts, right? So anytime I think of zeros, I think of x-intercepts. So again, as I look at this function here, it looks like we have an x plus 6 squared. So what that tells me is probably a touch and turn at -6, and there it is, right at that moment at -6. I see the x minus 7 is listed one time, so the function is most likely going to go through that x-axis. And as we see, we have a -6 twice and a 7 once. Versus over on the second function over here, we have x plus 6 squared and x minus 7 squared. So at -6, it's a touch and turn, and at +7, touch and turn. So we have real zeros of -6 and 7 twice. Now we're down here at the bottom discussing even multiplicity zeros, and right, that's something that happens an even number of times, so they're squares, right? Anything to the 4th, 6th, 8th power is just two big groups of 2, and so they're not going to allow the y value to change sign. So whether or not the entire piece is below or above the x-axis is dictated by the other factors. Now, since everything up on this one is squared, there's no way for negatives to come out of that function. The entire function is above the x-axis. All the y values that are going to spit out are positive. Versus over here, whatever comes out of this, if I put in, say, a negative x value of -8, this whole thing is guaranteed to be positive. But now what dictates whether the y value is negative or positive is really the x value as it pertains to -7. And so that's why this whole function doesn't come up to positive until it gets past 7. The rest of this function stays in negative y territory until that moment. Again, squares will always result in a positive output. So just barely touching the x-axis and turning back around, we say touch and turns or bounces. Again, for all these drawings, if you're not able to print this out, just give a quick sketch and just jot down some notes here, okay? So we're looking at, the thing that I would make sure I get is that this is an 8th degree polynomial. So this is an x to the 8th, right? It's not just x to the 8th, but, there's some other stuff here. And the highest exponent is the 8th degree. And so we want to list the polynomial zeros with their multiplicities. So first, let's go through and just sort of put some dots on it. So I think there's a 0 at 15. Looks like this one's at 10. Looks like this one's at 5. Looks like this one's at the origin. Looks like this one's at 10. And looks like this one's at 15. So as I count these things, right, I see 1, 2, 3, 4, 5, 6. But we have an 8th degree polynomial. So there must be some of these that count more than once. And when does that happen? It happens at that bounce moment. And so where do we have a bounce moment? I think we have a bounce right here, and I think we have a smaller sort of wider bounce right here. This is going right through. This is going right through, right through, right through. So if we have 1, 2, 3, 4 zeros that are going to count once, and then we have the 1, 2 here that count twice, right? So I think that if we add all that up, this gives us 4 onces and 2 twices, gives us 4 and 4. Oh, that's going to be 8. So let's go ahead and list them with their multiplicities. And so here they are. We have our negative 15 once, negative 10 with a multiplicity of 2. Negative 5 counts once, 0 goes through. At positive 10, it bounces, so that's going to be 10 with a multiplicity of 2, and then 15, it goes through. So that's 1, 2, 3, 4, 5, 6, 7, 8. That's 8 zeros, and this was an 8th degree polynomial. We have them all covered. So again, let's first go ahead and take a look at our zeros. We have one at negative 5 and one at positive 5. And just for the record, our y-intercept is down here. I always try to point out that y-intercept looks like it's about at negative 30, and I just don't like to forget any of the old stuff we used to talk about. So for certain, if it's y equals negative 30, this function is blah, 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 minus 30. So I just like to keep that in mind, that that's some useful information. Now focusing back on the zeros and their multiplicities, we have this idea of flexing at the x-axis. And so let's take a look first. At x equals 5, what happens? The function kind of bends, hits 5, and then goes to the opposite side. So it doesn't touch and turn. It doesn't go through nicely. It kind of pulls this little wonky move like this, right? And it kind of breezes by 5 there. So this is going to have a multiplicity of 3. More to come on that. Double back over here at negative 5. We know that that has a multiplicity of 2. So back on this idea of flexing, right? If this is a 5th degree polynomial, real roots of 5 and negative 5, this is going to be definitely a multiplicity of 2. And if it's a 5th degree polynomial, then I guess 5 minus 2 is going to give me a multiplicity of 3. So this has a multiplicity of 3. So we're going to have odd multiplicities, right? We're going to have this even multiplicity of 2, touch and turn, 1 straight through, and then when it's wonky like this, we're going to have that odd multiplicity. So we got touch and turn, straight through, and flexing. Crossing the graph, right? Crossing the x-axis, a multiplicity of 1, 0 crosses the x-axis. Flexing, right? The bendy part of the graph, an odd multiplicity 0 that flexes at the graph is a point of multiplicity of an odd multiplicity. And that multiplicity is going to be greater than 1. So it's going to be like 3, 5, 7, etc. But it's going to be an odd number greater than 1, because we know that 1 is reserved for crossing. Now, what happens if you get that odd flexing at some location that's either above or below the x-axis? So the flexing doesn't happen here. It doesn't happen on the x-axis, but it just happens some random point. Then that's probably the effect of imaginary zeros, right? I'm sorry for my writing here. There we go. You're looking at the effect of imaginary zeros, right? And you'd find them using the quadratic. And who's going to show up to the party? Oh yeah, your good friend, I. See, now this is all really coming together quite nicely. All right, so let's see if we can spot our friends without using any numbers, just speaking generically. So I have this x minus b squared, and so I know what you're thinking. You're thinking, well, isn't then the 0 of b positive? Well, not necessarily. B could be negative, and x minus that b could be x plus something, right? Here's what I do know. I do know that this picture has a touch and turn going one way or the other. I also know that it has a flex, right? So this here has a straight through and a touch and turn. So not that one. This one has just a flex, but no touch and turn. So it's not that one. This right here has two touches and turns, but no flex. Not that one. This must be our friend. Let's double check. A touch and turn here and a flex and turn there, or just a flex, I should say. So that must be our graph. So this is not really, in my opinion, it's easier to rule out than it is sometimes to find your culprit. If you rule out everybody that doesn't go, your final answer stands proud. So here's one with a little bit more work, right? We want to find the degree, the 7th degree polynomial corresponding to this. So what we're saying is we want to know f of x equals what? We want this polynomial in factored form. So we could do this. We know that we have x of -4 as of 0 with a multiplicity of 2. We also know that it flexes at -1. So we have a -1 with a multiplicity of 3. And another touch and turn right here at x equals 4 with a multiplicity of 2. So that's 2, 4, right? 2, 4, 5, 6, 7. That's our 7th degree polynomial. My apologies for the clanging and banging, but that means dinner's ready. I'll be right back. Now, knowing the zeros that we have, at this point, we can now use the fact that with a 0 of -4, we have a factor of x plus 4. With a 0 of +4, we have a factor of x minus 4. And with a 0 of -1, we have a factor of x plus 1. Then we use the fact that we have multiplicities, right? Turn and burns at the 4s. So that gives us our squares. And then the flexing at x plus 1, that gives us our x plus 1 to the 3rd. And so what's stopping us is not knowing a. So if only we knew an x and a y value to substitute in and solve for a. Well, lo and behold, we do. So what do? We go ahead and we substitute in -2 in for our y value. Don't forget f of x is just a fancy way of saying y. So we have our -2 is our y value. And then we're going to put 1 in for x in all those places. So we have -2 equals a times 1 plus 4 is 5 squared is 25. 1 plus 1 is 2 cubed is 8. 1 minus 4 is -3 squared is 9. And now we can solve for our a value. So this is 9 and this is a. And so a little bit of multiplication. 25 times 8 times 9 is 1800. So 1800a equals -2. So a is equal to -2 over 1800 or -1 over 900. So what do we do with all that? Well, we wanted to write this in factored form. All we needed was our a value and all the rest of the players stay. So let's write a final answer. Now, on a side note, this was a 7th degree polynomial, and it looks like it's coming down from the left and going down on the right. So a fashion like this. Now we know from previous lessons that this is an odd polynomial with a negative a, because if it was a positive a, it would go up like that, but it's not. So the negative fits quite nicely with the idea that it's coming, it goes out to the left, and as I move, as x, I should say, goes to negative infinity, y goes to positive infinity, and as x moves to positive infinity, y moves to negative infinity. That's an odd function, odd polynomial with a negative a value. All right, fits right in the schema of our previous learning. So negative 1 over 900, x plus 4 squared, that's our turn and burn there, x plus 1 to the cube, to the third power, that's our flex moment, and x minus 4 squared, that's our positive turn and burn right there. So there we go. That's our final answer to the 7th degree polynomial. That's a bit of work. As we approach the back end of this conversation, we want to discuss these inflection, these turning points, and what they create. So take this moment here. All the points on this side of that peak are lower, and all the points on this side of that peak are lower. At this moment, it is a local maximum. It's not the highest point of the entire function, but it is a high moment at that moment. So the red points are all lower than the blue. As opposed, say, if we put green marks on these lower humps, and we put like a little purple point at the bottom, those purple points are at the lowest point with respect to their area, meaning all of the green points over here are higher than the purple, and all of the green points over here are higher than the purple. And that is what we're saying. If you look right here, the y-coordinate is a local max if the point is higher than the nearby points, right? So this is a local max. Why? Because the blue, right? The blue guy right here is higher than all of the red points that are here. So there's a red point here, red point here, red point here, red point here. All those red points are lower than the blue. Conversely speaking, all the green points to the left and right of the purple points are higher. So the purple point is a local minimum, right? Because it's lower than all of the nearby points. And we refer to these local max and local mins when we're looking at those turning points. Now notice the turning point doesn't have to be on the x-axis. We're not talking about those multiplicity zeros, although that could be a moment where it's a local min, or it could be a moment where it's a local max. But anywhere where we take a turn could be a local min or max. Now we're going to turn our attention to the maximum number of turns a function could have, right? And this is what you want to grab in your notes, is this part right here, right? The graph of every polynomial of degree n has at most n minus 1 turning points. So if it's a degree 3, then n is equal to 3. So 3 minus 1 would be 2 turning points. All right? And TP stands for turning points, not Tom Petty. Once you get that in your notes, let's turn our attention to the schematic here. So we have a degree 2, 2 minus 1, 1 turn. Degree 3, 3 minus 1, 1, 2 turns. Degree 3 here, more dramatic double turn, right? So this looks like a flex, right? Whereas this is a through, through, and through. Okay, so 3 single zeros, 1 0 with a multiplicity of 3, right? So the number of zeros should agree with our degree. The number of turns is 1 less. Degree 4, all right, may see a flat turn like that, one big flattened bump, or you may see a 1, 2, 3 turns. So again, the maximum number of turns is going to be n minus 1, but it doesn't guarantee that I will always have n minus 1. For instance, 4 minus 1 is 3. I didn't see 3 turns here. I saw one big flat one. Down on the degree 5, looks like we have a flex there, right? So you're going to have, looks like the origin multiplicity of 5. And remember, we said that on a flex, it was going to be an odd greater than 1. So 3, 5, 7, and so on. Or a degree 5 could have one distinct distinct turn there, and then a long flattened turn there with a multiplicity of 4. And notice again, a turn and burn back up. So has to be squared or to the 4th or to the 6th, something even where it never crossed over that x-axis. Degree 5 again. All right, so we have 1 bend here, 2 bends here, 3 bends here, 4 bends there, degree 5. Hard to see in the diagram here, but this is a 6. So again, one big flat. Right, so anytime you see something that looks like an elongated sort of parabola, then that's got to be some sort of even degree. On the next one, sort of change colors here. It shows that we're exiting out on the same sides. So we got 1, 2, and then a long flat one here. So that's going to be a degree 6. Because of that flat one, I know that it can't be a degree 4 because that's an elongated flat piece. Or we could have 1, 2, 3, let's see, 1, 2, 3, 4, 5 turns, and that would be sort of more of a classical looking degree 6. Here we're looking for the minimum possible degree. So, sort of like x to the what? What's the smallest that number could be? Well, I know that I got 1, 2, 3, 4 distinct turns. It exits out on one side down and on the other side up. So I know that that's going to be an odd degree. And with 4 bends, I think the smallest it could be is the 5th, right? So I think this is a 5th degree. Now, who's to say it's not a 7th? Maybe one of these is a stretch. I'm not saying it's not, just saying that it has to be odd. And seeing that I have 1, 2, 3, 4 bends, well, if n minus 1 gets us any information, I guess with 4 bends, I'm going to get n is equal to 5. That's the minimum it could be. In the reverse kind of direction, or reverse thought process, I should say, what's the maximum number of turns? Well, the max number of turns is going to be n minus 1. So 5 minus 1, the maximum amount of turns is 4 turns. And with an x to the second, right, 1 turn, right? N minus 1 is going to give us 1. So 1 turn there and 4 turns on the part A. All right, and that brings us to our last slide. So in our last example here, it says, given that the polynomial is of degree 6, which of the following could be its graph? Well, I know that since it's even, right, I'm looking for something that ends in the same direction for n behavior. It's either both up or both out. So it looks like G is odd, right? This goes out this way and out this way. Nope. And D also, no good. Now, who else could I rule out? When looking at B, it looks like I see 1, 2, 3, 4, 5, 6 turns. I'm not even going to keep counting. It can't have more than 5 turns, so B is out. Remember, n minus 1 is going to give us our max number of turns. So 6 minus 1 is equal to 5. So that's going to be the maximum number of bends. Also, F seems to be 1, 2, 3, a flex, 4, 5. So I think we have 6 here. So I'd say most likely not that guy. Our A value, or A graph, I should say, seems to just be a big swoop, not a flat. So we're going to go ahead and cross that off. That looks pretty much like a parabola. On H, this looks like a flex and then another flex here. So that has to have a minimum multiplicity of 3. So if that's 3 and that's 3, perhaps those are our zeros. So this could be a culprit. Also over here, we could have one turn here, two turns here, and then a big even one there. That could be also counting for two bends. So that could be it. And then E has a singular long flat piece. And I'm going to leave it at which of the following could be? Well, I think C could be. I think that H could be. And I think that F could be. For the red boxes, I'm not saying that they're, I'm not saying that they're guaranteed not. I'm just saying that they're most likely not. So the red box is most likely not. The blue X is definitely not. E, C, and H, those are our most likely candidates. So in closing, make sure that these things are not just in your notes, but that you understand them. All right. And if there's questions, I will address them during our live conference, and we can go from there. All right. Thanks for taking good quality notes and listening to me drone on and on about polynomial behavior. See you next time around.